finish this up if I can find my second. Okay, so sine x prime is cosine x, negative sine x. You can give it a shot and try it. You have to use a lot of identities from trig and you will get it. Now I want to determine tangent prime, not with the definition. So tangent prime is sine x over cosine x prime. We have the quotient rule. Now we can determine this, and we don't need anyone to tell us what it equals to. So please dictate the quotient rule. Sine prime, cosine x times cosine x minus sine times cosine x prime. I'm going to change this. Divided by cosine x squared. But the top is cosine squared plus sine squared. That's another identity, trig identity. What does that equal to? 1. Thank you. 1 over cosine x everything squared, which is, what does 1 over cosine equal to? Secant. Very good. So it's secant squared. So now we know, I go back to my handout, tangent prime is secant squared. In the same way, we can determine the other ones. Cotangent will be negative cosecant squared. Secant prime is secant tangent. And cosecant prime is negative cosecant, negative cosecant cotangent x. Let's prove one more, whichever you want. So we proved sine, we proved tangent. Let's choose one more from here, whichever you prefer. Secant, we want to prove secant. Very good. So let's look at secant. So we want to find secant prime, which is 1 over cosine. And I have to use the quotient rule. 1 prime, 0. You don't have to write this, times cosine x minus 1 times cosine x prime. So it changed that into positive over cosine x squared. This is gone. So now I have another little algebraic manipulation. Sine x over cosine x times 1 over cosine x. I split the fraction sine over cosine squared into sine over cosine times 1 over cosine. So I know what this is. I know what this is. So then I know now that secant prime is secant tangent. Secant tangent. In the same way we determine the other ones. And I think we can finish up now this section by quickly finding f prime of x. So what would you say? So we have f of x equals 3 sine x minus 4 cosine x. And what would you say for f prime? Three cosine x plus 4 sine x. Very good, excellent. Here's the next one. F of x equals x squared times cosine x. We want to find f prime. The last problem, since we already did like 2 problems today, they are very similar. I would like you to turn it in with Maple. Perform the calculations by hand first. Calculate, determine the tangent, and then show me a little graph in which you show that the tangent is tangent to the curve with Maple. Okay? So we're going to work on the other 3. So how do I differentiate x squared times cosine x? First function prime, 2x times cosine x plus x squared times negative sine x. So 2x cosine x minus x squared sine x. Okay, let's work on, any questions on this? Let's work on tangent x over x squared. So we have f of x, which is tangent x over x squared. This is the quotient rule. Or you can change it into x to negative 2 times tangent x and use the product rule. It's up to you. You tell me what you would like to do. Product rule or quotient rule? Okay, perfect. So f prime of x, top function prime. Tangent prime is secant squared multiplied by x squared. I'll put it in front because I don't like to put anything after secant. And then minus top function times the bottom prime. So I will write 2x times tangent x divided by x to the fourth. Yes, I will have to factor out x and simplify it. Okay, I cannot finish this before I take x out. X times secant squared x minus 2 tangent x over x to the fourth, and I'll take 1 away from the top and from the bottom. So the simplified form has x to the third in the denominator and x secant squared x minus 2 tangent x. Any questions? Any questions? Okay, last problem in 3.3. So f of x equals x cosecant x plus 6 cosine x tangent x. F prime of x. Tell me when you're ready. They are both, this is a sum of two products. I have to use the product rule on all of them. On both of them. So first function prime is 1 times cosecant x plus x times cosecant prime. Negative cosecant times cotangent plus 6 can wait outside. Cosine prime, negative sine x times tangent x plus cosine times tangent prime. I will try and see if I can simplify it a little bit. I'll attempt that. So one more time. First function prime is 1 times the second function plus the first function times the second one prime plus 6 outside. I don't like to get bothered by a constant. Cosine prime times tangent plus cosine times tangent prime. So let's see if we can do anything. Cosecant x minus x cosecant x times cotangent x minus 6 sine x tangent x plus 6 cosine x secant squared x. I could simplify here because this is 1 over cosine squared. Cosecant 1 over sine and cosine over sine, not that much. It can stay as is. There's nothing else we need to do. Okay, let's go back to, let's continue with 3.4, the chain rule. Any questions for me here? Any questions? So 3.4. The chain rule. When we differentiate x to the fourth power, we get 4 times x to the third, correct? Times, I should have written this, x prime. The reason why we did not write this is because this equals 1. That's the only reason why we did not write it. So now I could have a function composition, which is f of g of x, as we know from algebra. So I have a function inside another function. Here, you could say, I kind of did not have one function inside of another, because x prime is plain, yes, so it's just plain x, right? But I could have, instead of x, I could have, for example, x to the third. So if I have a function of x to the third, like, for example, let's say I have the square root of x to the third. So I have the outer function, that is f. I have the inner function, that is g. So this is no longer a plain function, like I had x to the fourth. It has an outer, which is the square root, and it has the inner, which is x cubed. You can say yes, but for this function, you can change it into x raised to 3 over 2, and I have no problem differentiating in the same way. I would have to agree. Now, what if I have this function? So what if my g now is x plus 1 to the 5th power? And I want to differentiate the square root of x plus 1 to the 5th power. You could say no problem, x plus 1 to 5 halves. Still, but I still have another function in here. And if I make it a little bit more difficult, let's say I have x squared plus 1 to the 5th power, and now I want to take the square root from it. So now this is x squared plus 1 to 5 halves. How do I differentiate this? If this were just x, I would have said 5 halves times x to 5 halves minus 1, and I'm done. But this is not plain x. So now when I differentiate, and I'm coming back to the handout that I gave you. When I differentiate something like this, I have to differentiate the outer function first, and then multiply by the inner function prime. So see, if this were just x, again, I would say 5 halves plus times x to 5 halves minus 1. But now I have to continue times the inner function prime. So one more time. F cum g prime is f prime of g times g prime, because this is no longer plain x. So this is the chain rule. Chain rule. So we differentiate the outer function times the inner function prime. Now I may have a function raised to a power. Here I'm combining the power rule with the chain rule. If this is plain x, I will say n times x to n minus 1, and I'm done. But it's not plain x. It can be any complicated function. What do you think the answer would be? I still bring n in front. I still have f raised to n minus 1, but since this is not plain x, I have to multiply the answer by, say it again, f prime. Right? We don't differentiate the exponent. I'm not sure if you said n or f. Is this clear? So one more time, if this is just plain x, this portion disappears, because x prime is 1. But this is not plain x. So this is a function, like this one. So when I differentiate this, and we're going to do it right now, and then we'll look at other examples, I'm going to have 5 halves, x squared plus 1 to 5 halves minus 1, times x squared plus 1 prime. Okay, so let's do that. First function. So we have x squared plus 1 raised to 5 halves, and we want to differentiate this. It's basically this rule. What will you tell me to write? 5 over 2 times x squared plus 1 raised to 5 over 2 minus 2 over 2, 3 over 2, times, I cannot stop, it's all multiplied, no addition, in the chain rule, no addition, 2x, very good, indeed, times the inner function prime, excellent. And I will simplify this with this, and I have 5x outside, x squared plus 1 to 3/2, and that's good enough. Now, some situations can get hairy, right? These are not that difficult. I would like to discuss this for sure. This is a must. But please choose from here whatever you want. If you say all of them, we'll work on all of them. A. Okay, so in A we have x squared minus 6x, everything to the 4th power. And we want to differentiate this. What will you write? Yes. Quantity. To which power? Very good. Multiplied by. That's it. Indeed, 2x minus 6. Yes, I can clean it up a little bit. I can remove an x from here. I can remove a 2 from here. It is recommended to do this. So first I factor out an x inside, and I did not take it to the 3rd power yet. And then I factor out the 2 here. 2 times 4 will be 8. I can put x minus 3 in front, but then x gets cubed, and x minus 6 gets cubed. And this is the final form. 8x cubed, x minus 3, x minus 6 to the 3rd power. This is preferred as the fully simplified form of this expression, of this derivative. Any questions? Go ahead. Please, Tony.
When we're coming to like a right or wrong answer, we have to simplify that all the way to
You'll see what happens in chapter 4.
Okay.
Yeah, it's a preparation for chapter 4.
Got it.
Okay. Okay, next one. Which one is next? This will be changed into 6 to x to the 3rd minus 4x plus 3 raised to negative 5, and it's basically the same thing. Times the inner function prime. This one looks awful, right? Can we handle this one, or and we move on to C or not? Yes? So this is exactly like this. So you bring down, you have down negative 5, so you have negative 30 times this to negative 6 times the inner function prime. And you will not be able to do anything else. Is that okay? Everyone? Yes? Okay, let's work on C. So this is the cube root of x squared plus the cube root of x. There are many functions in here. I can't say there is just one outer function and one inner function. I can't say that. It wouldn't be true. So first I'm going to rearrange this a little bit. I'm going to say x squared plus the cube root of x to 1/3. And maybe go even further and write x to 1/3 inside to 1/3. So this is almost a necessary prep before I differentiate. In other words, I change the cube root into whatever to power 1/3. And now let's see what we have. So I want to differentiate x squared plus x to 1/3, everything to 1/3, and everything prime. So remember, I have a function raised to a power. I'm coming back to the power rule combined with the chain rule. A function raised to a power is n times the function to n minus 1 times the inner function prime, this function prime. So what will I write first? Very good, excellent. And x squared plus x to 1/3 to which power? From 1/3 I subtract 1, so that has to be negative 2/3. So all I did so far, allow me to go back, all I did was so far was I brought n in front and I subtracted 1 from the power of this function. Now I'm here. This is the inner function prime. This is the inner and this is the outer, the inner function prime. So now this is my inner function and I have to differentiate it. That's the outer. So now multiplied by, very good, plus 1/3 in front, x2, that's it. Don't try to do anything here, this is good enough. So it looked difficult, but once we broke it down into pieces, then any questions here? Tony, go ahead.
In the situation where we have something like this and this works, but our textbook has it simplified as the correct.
I doubt that they will go any further from here.
Okay.
They may change the negative exponents to positive exponents, but they cannot really do much.
Okay.
Yeah. Okay. Sine to the 4th of 5x. Sine to the 4th of 5x. How many functions I see here? I see power 4. I see function sine. And I see function 5x. So I see power 4 is the outer. Then the next level is sine. And then the innermost is 5x. Right? Because if I ask you to evaluate this function for x equals 1, you will first have to perform 5 times 1. Then you will have to apply sine to that. And then the answer is gets raised to the 4th power. When we differentiate, we go exactly backwards. So I said power is the last, sine was number 2, and 5x was number 1, right? 5x is first when I evaluate, sine is the second, and then power. I have to go backwards. Power, sine, 5x. So I have to differentiate the power first. What do I get? And it's all product. 4 times sine to the 3rd of 5x times the next level. Level second is sine. I have to differentiate sine. Cosine of 5x. And now the 3rd level. I'm at the innermost function. Very good. So the simplified form, and no one can do anything else, is 20 sine to the 3rd cosine of the angle. So one more time. So when I differentiate, I go backwards. When I evaluate, I perform 5x, then I apply sine, and then I finish with the 4th power. When I differentiate, I go backwards. I start with the 4th power. I continue with sine, and I end with 5x. Okay, so this is a product. This is a ratio of sine and tangent, and this I have to do. So if you say you can do these two at home, that's fine. If not, please choose, but I have to show this. And this is directly connected to what we cover in pre-calculus.
We do F.
Yes. So let's do F, in which we have sine 2x over tangent 5x. Sine 2x over tangent 5x. Quotient rule combined with the chain rule, because this is not sine x over tangent x. It's sine of twice x, which is a function, over tangent of 5x, which is another function. So top prime is cosine 2x multiplied by the inner function prime, which is 2, multiplied by the denominator, minus sine. Of course, I ran out of room. I always run out of room. No question and no doubt in there. Sorry about that. I have to copy it. So I have cosine twice x multiplied by 2 multiplied by 5 tangent 5x minus, I copy the top, multiplied by tangent prime, which is secant squared 5x, times the inner function prime, which is 5, over tangent 5x, everything squared. Don't try to do anything here. We don't care. We really don't. The only thing you can do is just put the 2 in front, and I recommend that, and put the 5 in front, but nothing else. So just put 2 in front because constants go in front, and nothing else. Now we have to talk about the last one here, g. So f of x equals x squared minus 5 raised to negative 3 over 3x minus 1 to negative 4. I refuse to apply the quotient rule on this problem before I simplify it. Is there any way I can do to simplify this expression or this function? It has both negative exponents, top and bottom. I don't want to work with negative numbers. Is there any way I can rewrite it somehow with positive exponents? Exactly, 1 over, you're right, but we end up with this. This is more human. Of course, you'll get the same answer. The point I'm making is try always to simplify if you can. So now I'm trying to find the derivative of this. And tell me when you are ready. And this has to be simplified fully. The top function prime, 4, 3x minus 1 to the third times, very good, times the denominator, which is this, minus the top times the denominator prime. Can anyone give us a denominator prime? Very good. To the second power times. I would have stopped if that quantity would have been x, but I can't stop. And I have to continue with, very good, over x squared minus 5 to the, exactly, 6th power. Now, there's a lot of work to do next. I will simplify a little bit by rearranging this into 12, 3x minus 1 to the third, x squared minus 5 to the third, minus 6x, 3x minus 1 to the fourth, x squared minus 5 squared, everything over x squared minus 5 to the 6th. So now, I'm looking at how many terms do I see at the top? Two terms, very good. This is one, and this is the other. Perfect. So now I would like you to factor out the greatest common factor coming out from the top 2 terms. And I'm ready when you are. Definitely a 6. What else? To which power? With, very good, excellent. What else? Very good. To the second power. Excellent. Let's see what is left from the first term. 2 is left. What else? Very good. And I reached this. Excellent. Great. 6 is out, but there is an x left. From 4, I took 3 away. So I have 3x minus 1. And from x squared minus 5 squared, x squared minus 5 squared, what is left? 1. Excellent. Good. Look what I'm going to do next. That's why this is mandatory. You remember these problems, Ben, from pre-calc? Those handouts, that's what they're for. So this is 6, 3x minus 1 to the third, and now I have to distribute here. 2x squared minus 10 minus 3x squared plus x. That's what we did this in pre-calc. For this. Yes, I'll combine like terms in here. Nothing else simplifies. I will factor out the negative leading coefficient if I get a negative leading coefficient in a moment. So this is indeed negative x squared plus x minus 10 over x squared minus 5 to the fourth. And I see a negative leading coefficient. I will put it in front. 6, 3x minus 1 to the third, x squared minus x plus 10. When I factor negative 1, I have to factor out from all 3 terms. X squared minus 5 to the fourth. This is the best result or simplified form for our function. Any questions? I'd like to finish this section with problem 2 here on the back of 3.4 of the chain rule before we move on. Any questions on this problem? And yes, of course, just one example like this is not going to build confidence, right? So that's why I want you to work on all these problems and come back and say, I still need help on such and such. But if you don't work on these problems, you will not know where we have to insist. Okay? So let's look at the following. Now, let me look at a couple. Yes, Tony?
Are all of 3.3 and 3.4 due Wednesday?
As soon as possible, because I have to move on. Yes. Now, at least, so it's a very good question. 15 to 50 odd, so that's 40 problems. Divided by 2 is 20 problems. Do at least 10 of those, and you can do the rest later. So you can ask questions. If you see 5 problems that are the same, just do 2 of those and move on to the other ones.
Okay.
I'm okay if you say, okay, these seemed very similar to me, and I'm okay. So 1 to 13 basically is 6 problems, because it's just the odd number problems, and see the answer in the back.
Yep.
And then come back and say, I still haven't gotten this or that. Okay? So concerning notation, I want to explain that f prime has different notations, not just f prime. So y is the same thing with f of x. So another notation, which is the so-called Leibniz notation, is dy over dx, the derivative of y with respect to x. Another notation would be d over dx of f, or f of x. Same thing, the derivative with respect to x of f of x. We are going to use at least these two quite frequently, interchangeably. They are the same thing. Okay. So now we are given that y equals u to the third plus 4u squared. And we are told that u equals 3x squared minus 4x. Okay, and we are asked to find dy over dx. So find dy over dx. So, and it says in two different ways. Find it in two different ways. Here's one way. So first of all, I want to say what this is telling us. What is this telling us? I am really told here that that y is a function of u, but u is not a variable. U is a function of a variable x. So in order to find dy over dx, so dy over dx, I'm really differentiating u y comp u of x prime. This is what I have to differentiate. So y is the outer function, and u is the inner function. So I can write this, if I continue here, I can write in the following way. dy with respect to u, so I differentiate the outer function with respect to u, but then I have to multiply by du differentiated with respect to x. So this is the first way, first possible way. The second possible way would be to write y equals u to the third plus 4u squared equals, I replace u by 3x squared minus 4x, and I raise it to the third plus 4, 3x squared minus 4x, and I raise it to the second power. So this is my second way. My first way would be not to plug it in, but just keep it as f prime of g times g prime. The second possible way is I say, fine, I have a function y of u, but u is a function of x. I'm just going to plug it in, and now y is a function of x, and I'm done. I don't even have to think of u at all because I replaced it. I replaced it in y. I replaced u in y by what it equals to. So these are the two possible ways. So let's start with the second one because I already have it here. So y prime or dy over dx will equal, how will I differentiate this? Now this is a sum. So I have to differentiate this piece and this piece using the chain rule. So I have 3. I have 3x squared minus 4x to the second power multiplied by the inner function prime, 6x minus 4 plus 8 indeed. 3x squared minus 4x to the first multiplied by the inner function prime, 6x minus 4. This is just the second way. I noticed something. I noticed that 3x squared minus 4x as well as 6x minus 4, I could factor out a 2 in there. In a minute I will. Can be factored out. So from the first term, I factored out at 3x squared minus 4x and a 6x minus 4. I still have a 3, and I still have one of these two. Would you agree? So 3 and 3x squared minus 4x. And plus what? These two are in front. So what is left from here? 8. And finally, I can factor out an x, and I get 3x minus 4. I can factor out a 2, and I get 3x minus 2. And I'll perform the operations inside as 9x squared minus 12x plus 8. And there is nothing else I can do. I will just put the 2 in front. 2x, 3x minus 4, 3x minus 2, 9x squared minus 12x plus 8. Any questions? Any questions on this? I have to come back to the first method now. Any questions on the second method? So one more time, what did we do with the second method? I said, okay, y equals this, fine, but u equals this. So I plugged it in. And I differentiated using the power rule and the chain rule for both. And I realized that they have a common factor, and this was the common factor, and then I distributed, and these were the leftovers from each term, and finally I got this. Here's the second way. I will differentiate y with respect to u, and then I will differentiate u with respect to x. So let's go back. dy over dx. Oops, I didn't mean that. Sorry. Okay. So dy with respect to u. So what will you tell me to write? Look at y and differentiate it with respect to u. That's why I went back. What do we get? 3u squared plus, very good, 8u. So 3, it's not good. 3u squared plus 8u times, so this is dy differentiate with respect to u. Now I want du with respect to x times du with respect to x minus, good. I can leave it like this. I can have u and x in the same expression. So what will I have to do next? This is okay. But what will I have to do here? Plug it in. Plug it in. So I will have 3 in parentheses 3x squared minus 4x squared, and then plus 8, 3x squared minus 4x times 6x minus 4. Okay, so now I have to factor out a 3x squared minus 4x from the two terms inside, right? And I rushed again. Sorry about that. And I have to take out 3x squared minus 4x. 3x squared minus 4x. Good. So I took out a 3x squared minus 4x, and I have a 3 times 3x squared minus 4x. And then I took this out, and I have plus 8. Agreed so far? Okay. So then I will factor out an x here, and I have 3x minus 4. I will factor out a 2 here, times 2, 3x minus 2. I will distribute 9x squared minus 12x plus 8. And finally, I put 2x in front, 3x minus 4, 3x minus 2, 9x squared minus 12x plus 8. Any questions? Any questions? And they have to be the same. I know I only have roughly 10 minutes. Any questions for me? Any questions? Is it clear what just happened? It's all algebra. Okay. Okay. Now, I would like to continue. I'll stop in 10 minutes, promise. I would like to talk about implicit differentiation and what it means. Maybe before we do that, I just want to ask you, what about differentiating e raised to a function of x? And also a raised to a function of x prime. To establish this before moving on. E to u. The inner function prime, which is when I try to evaluate this, I have to evaluate u first and then apply this. So this is the outer and this is the inner. So I'm going backwards. First the outer times the inner. What about a raised to u to the x prime? It's a to u to the x times, remember, natural log a times the inner function prime, which will be which one is the inner? U prime of x. Very good. Okay, so let's talk about implicit differentiation. Okay, and let me give you an example. I'm going to make one up, and then we'll go to all of these. So this is section 3.5, implicit differentiation. Such a long word. Okay, so let's say I have y to the third plus 2y squared minus 7x squared plus 5. Okay, well, let's say I have that equals 0. From this equation, I would like to determine dy over dx. What am I telling you when I'm asking you to find dy over dx? What am I really implying? That y is a function. Once I say find dy over dx, it's very clear that y is a function of course, perfect. So then I'm asking you, solve this for y. And the answer is no one can. So I cannot give you an f of x or y explicitly. I don't have it. I can't solve that. Even if I cannot give you y explicitly because I have no way of solving this equation, we can still find dy over dx. Or to be exact, an expression for dy over dx. It will depend on y. But I will have an expression for the derivative. A question for you. If I want to solve the equation the square root of x plus 1 equals 5, what am I trying to do here? How do I solve this equation? What will I have to do to both sides? Right, obviously. Well, in order to determine dy over dx, I'm allowed to differentiate both sides. Like I did here, by squaring both sides, I'm allowed to differentiate both sides of an equation. And I will get dy over dx. So now let's differentiate the right-hand side. And you can say, well, the right-hand side will be 0. Well, let's differentiate the left-hand side. This is the inner function, and this is the outer function. Inner function, outer function. And this is just a variable. So how will I differentiate y to the third? And I highly recommend, when it comes to implicit differentiation, do not use f prime or y prime. Use the notation dy over dx. It will get so confusing, and if you forget that little thing, then you will mess up the problem. It is safe to use dy over dx notation in implicit differentiation. I will always use that. So please differentiate for us y cubed. Maybe I should make it a little bit more difficult here. I'm going to put an y in there. So y cubed, 3 times y squared times the inner function prime, dy over dx. Let's come back to our definition, if I can find it quickly. Yes, I found it. Y to the third prime is 3. Y to 2 minus 1 times y prime. 3. Y to the second power times y prime. Instead of writing y prime, I choose this notation. Plus 2y squared prime. For y to power 1 times the inner function prime. And now, of course, I ran out of room. I always do. So now I have a product. I reached the product. Negative 7x squared is a function, and y is another function. So what do I do next? So put minus, and in parentheses, because I don't want to mess with 7. I don't care for it just now. I differentiate x squared, and I get 2x times y plus x squared times the second function prime. What is it? Very good. Plus 5 prime. How much is 5 prime? 0. Equals 0. Okay, I'm going to distribute negative 7. So I have 3y squared dy over dx plus 4y dy over dx minus 14xy minus 7x squared dy over dx is 0. And here's your hint. Remember, I am after dy over dx. What should I do next? Exactly. I must factor out dy over dx. And I must move this to the other side. So what is left in parentheses when I pull dy over dx from these 3 terms? Yes, this did not have the variable, so I moved it to the other side. Final step, please. And this is how we deal with implicit differentiation. Dy over dx equals what? Indeed, this over that. 14xy, 3y squared, plus 4y, minus 7x squared. And you can say, okay, you're just blinding us, right? You solve for dy over dx, but you still have y in there that is a function that you don't have. True. I can only determine an expression for dy over dx, but I cannot determine it because I don't have y. But I could be asked to evaluate this or find the rate of change of y with respect to x for x equals and y equals. And then I will get a number. And that is very valuable. Although I don't have this expression, if I have a point, x comma y, of course, x comma y has to work here. When I plug in x and y, I have to get 0. Otherwise, x comma y doesn't have, that's why I don't have a number. I just made the problem up a second ago. So once I have x and y, and I plug them in here, I will say, although I don't have y, I can tell you the rate of change of y with respect to x at point blah, because I can plug it in and give you the number. So that's the use of